This video is going to look at example 3 of your parametric equations day 2 notes. Specifically in example 3, we're looking at this idea of projectile motion. So you can kind of think about this as some object is being hit or thrown up in the air and it's falling back down. Okay, specifically in this example, we see that Marshall hits a golf ball. Okay, so you can call this little circle here our golf ball. He's hitting that with an initial velocity of 150 feet per second. And he's doing so at an angle to the horizontal, so this could be like our golf course or our grass, of 30 degrees. Okay, and it should hopefully make sense to you guys that this golf ball is being hit up into the air and it's returning back down to the ground. Okay, so there's a bunch of questions. As you can see, there's 4 questions that we're going to answer using this information. But before we do so, we need to unpack a little bit of notation. So all of this stuff that's written here in black is detailed in the answer key of your notes, of your guided notes. Or actually just your guided notes, sorry, and as well as the answer key. But this is all typed out for you, and this is information that we're giving you. We're not expecting you to know this yet. So I'm going to take a few minutes to take this all in. So we have this notation here, h sub 0. This is the initial height of our object, in this case a golf ball, and it's measured using some unit of distance. So because we were told that Marshall hits this golf ball at an initial velocity of feet per second, we know that our measurement of height down here is going to be in feet. Okay, we also have this idea of initial velocity of our object. Okay, again, in this case, it's going to be measured in feet per second, but it will always be some unit of distance and some unit of time. In this case, we were told that v sub 0, our initial velocity, v sub 0, is equal to 150 feet per second. We'll come back to that in a little bit. We are also going to need to consider some angle measure, theta, which is the angle of projection. Okay, another way to think about this is the angle at which our object is launched. Okay, the last thing that we need to look at is this number right here, and I'm going to actually box it so you don't accidentally see that symbol as a hash mark. That's actually a negative. Okay, we have this constant negative 16 feet per second squared. Okay, and this is the effect of gravity on the object. Okay, this is what's causing that golf ball to launch up into the air and then fall back down. Okay, so again, these are just some new notations, not necessarily new, right? We've seen theta before, but it's important to understand what h sub 0, v sub 0 means, and we'll see this negative 16 here in a second. Okay, another piece of information that you're given on your notes is 2 equations that we're going to use to help us model the distance that the object has traveled. And this kind of fits with our parametric studies, right? Because we have this idea of measuring in the horizontal distance using an x equals equation, and in the vertical distance using a y equals equation. So let's take a closer look at that horizontal distance equation. Our horizontal distance equation is defined to be x, which should make sense, and it is our initial velocity times the cosine of our angle of projection, which again makes sense, right? Cosine typically, well, doesn't typically, cosine and x go hand in hand. And then we have measurement of t, right, times t. So initial velocity, cosine of our angle of projection times our variable t. So this is our parametric equation, x of t. Okay, our vertical distance is defined using a y equals equation, right, which should make sense, negative 16t squared. Now I want to talk about this for a second. That negative 16 is that effect on gravity, and that t squared is giving us that parabolic shape. So if you look back up to my little drawing here, we have that negative parabola, right? So the negative 16t squared is giving us this shape, right? This general shape. Now, how steep or how wide that is kind of dependent on some other factors in the equation. Okay, so carrying on and unpacking this equation, again, we have y equals negative 16t squared plus our initial velocity times sine, which sine is matching with y, so things are kind of checking out there. Sine of our angle of projection times t, and then we have this initial height, which should make sense, right? We're hitting something or throwing something or dropping something from a certain height, and we're measuring kind of the path and the change in height from that initial height. Okay, so we haven't even started looking at the problems yet, and that's okay. There's a lot to kind of unpack here. So let's refresh ourselves on what's actually going on. Again, we're looking at Marshall hitting a golf ball with an initial velocity of 150 feet per second at an angle of 30 degrees to the horizontal. Question A asks us to find the parametric equations that describe the position of the ball as a function of time. So I already made the note here above that horizontal distance that this is our x of t equation, and I left off here, I didn't mean to, but this is our y of t equation, right? We're going to take the given information and fill it into these two equations in order to answer part A, in order to find the parametric equations that describe the position of the ball as a function of time. Okay, so again, we just need to go ahead and fill out these equations. This x of t equals velocity initial cosine of theta times our variable t, as well as y of t, which is negative 16t squared, plus initial velocity sine of our angle of projection times t, plus our initial height. So as a reminder, we read up here that our velocity was 100, our initial velocity, right? We're given it here, our initial velocity of 150 feet per second, okay? So we can plug that in to the appropriate places in our equations, right? In our x of t equation, that'll be our coefficient to cosine, and in our y of t equation, that'll be our coefficient to sine. We are also told that Marshall hit this golf ball with an angle of 30 degrees to the horizontal. So that will replace our theta in both equations. So we'll take this cosine of 30 and sine of 30. The last thing that we need to consider that would be something that could possibly be a value, right, not a variable, would be this initial height. Now, there's no indication that the ball was hit from a tee, so we're okay to assume that it was hit from the ground. And so our initial height is just 0. So let's go ahead and finish writing these equations. We're going to see, plugging in those values, that x is equal to 150, right, our initial velocity, cosine of 30 times our variable t. Now, we want to actually be working with this equation and doing some analysis and evaluation with this equation, so it would be helpful to go ahead and simplify this statement, right? We know at this point that cosine of 30 degrees is square root of 3 over 2, and then we still have that times t. And that can simplify a bit, right? We can divide 2 into 150 to get 75. So we're left with the parametric equation x equals 75 square root of 3 times t. It's parametric because it is our rectangular measure, right? Our rectangular horizontal measure x defined in terms of t, in terms of that parameter t. Okay, so again, just a quick refresher, our v sub 0, our 150, our initial velocity got plugged in as our coefficient to our cosine, and then our argument to our cosine was our angle of projection, that 30 degrees there, and we were able to simplify. Okay, so we'll go ahead and do something similar here with our vertical distance equation. That tells us that we have y equals negative 16t squared plus our initial velocity of 150. I'm going to go ahead and erase these notes here, but remember that our initial height is 0 and think about y. So 150 sine of 30 degrees times t. And again, we can do some simplifying. We'll see that this is y equals negative 16 t squared plus 150 sine of 30 degrees is going to be 1/2. And then we have multiplied by our variable t. Remember, there's this plus 0 at the end, right? That initial height of 0, but we don't need to write that down every time. So our vertical distance equation, our parametric equation describing the vertical distance of our golf ball is y equals negative 16 t squared plus 75t, where that 75 is coming from that simplification here of that 150 times 1/2. Okay, so that answers part A, which asked us to find the parametric equations that describe the position of the ball as a function of time. Okay, we have our horizontal equation here describing the position of our ball given a certain amount of time, and then our vertical over here. Okay, part B, it says how long was the golf ball in the air? Okay, so we want to go ahead and think carefully about what equation or what information is going to be helpful here, right? We have that we want to know for how long, what quantity of t was the golf ball in the air. Okay, so we know that the golf ball started on the ground. Okay, it was hit up and it falls back down. So basically what we're doing, if we think about this graphically, our golf ball was on the ground, it got hit up and it fell back down. So we're looking for this spot, right? We're looking for our height again to be 0. Okay, it was 0 initially, but now we're looking for how long after it was hit was it 0 again. Okay, so we're going to use the height equation. We want to know when is the height. What part B is asking us is when is the height or our vertical distance zero. Okay, so I want to know when is negative 16 t squared plus 75 t equal to 0. And all of a sudden, just writing that out, right, like translating that for myself, I see a quadratic that I need to solve. Okay, it's a 2-term quadratic with a common factor of t that I can go ahead and factor out. I find that that is t times negative 16t plus 75 equals 0. Here we can go ahead and use the zero product property to solve. We know that when t was equal to 0, we had a height of 0, and that checks out with like this problem situation, right? We started hitting the golf ball from the ground, and then we also know that negative 16t plus 75, that's the solution to that also gives us a height of 0. So solving this gives us negative 16t equals negative 75, or that t equals 75 over 16, which is roughly 4.688 seconds. Okay, so we know that when we hit this golf ball, right, we hit it from the ground, it landed back on the ground, that was t equals 4.688 seconds. Okay, so it was in the air for about just under 5 seconds there, given this initial velocity and angle of projection. Okay, so part C is asking us for the maximum height of the golf ball. So, well, it's actually asking when was the ball at its maximum height, and we also want to determine the height of the golf ball, the maximum height of the golf ball. So if we look back up at our picture, the maximum height is going to be right here. Okay, so thinking about thinking about our studies of quadratics and parabolas, this is happening at the vertex, right? The maximum height of our golf ball is happening at the vertex of our parabola. So we need to remind ourselves that to find the vertex given the equation of our parabola, we're going to rely on this equation, x equals negative b over 2a. And that's something that came from our studies of quadratics, right? If we have a quadratic equation, ax squared plus bx plus c, we can go ahead and find the x coordinate of our vertex by taking the b value and plugging it into the numerator here, and then our a value and plugging it into the denominator here, okay? So we're going to steal that vertical distance equation, that y equals negative 16 t squared plus 75t, and we're going to go ahead and substitute in the appropriate values. The negative 16 is our a, and the 75 is our b value. So when this is happening, that x value at which this is happening is x equals negative 75 times 2 over a, which is negative 16. Okay, so our golf ball is hitting its maximum height at a time of 2.344 seconds. And notice that's only half of what question C asked us, right? We're asked when this happened, and we're also asked what is the maximum height. Okay, so to figure out what the maximum height is, we'll go ahead and plug in that value. We'll evaluate our vertical distance function, right? Our function that is defining the vertical distance or the height of our golf ball. We're going to go ahead and plug in that 2.344 measure of time to figure out what the maximum height is, right? Basically, what is the y value of our vertex, okay? And we find that that is roughly, when you go ahead and plug that into your calculator, that is roughly 87.891 feet, okay? So both of those pieces of information are our answer to part C, okay? Previously, that 4.688 seconds, that is telling us how long it was in the air, right? That's kind of like our x-intercept if we think about that graphically. Okay, so part D, this last part, and thank goodness because I'm almost out of room, part D is asking us for the total distance the golf ball traveled. Okay, so the total distance that it traveled, we're thinking about from where it started to where it ended. Not necessarily the arc that it followed, but how far away is its starting point and its ending point. So part D is actually going to use our horizontal distance equation, because again, we want to figure out how far away the golf ball lands from where it started. We already know from part B that the golf ball lands on the ground at, let's see, what was it? That was 4.688 seconds. So we're going to utilize this value here to help us figure out how many feet it traveled away from its starting point in that amount of time. So we can plug that value, that 4.688 seconds, into our horizontal distance equation. Okay, so in solving part D, we'll go ahead and take our horizontal equation and substitute in the appropriate value, right? The amount of time it takes until our golf ball hits the ground again. So that 4.688, which tells us that after 4.688 seconds of being in the air, the golf ball lands 608.92 feet away from where it started. Okay, I apologize about how kind of crammed that got, but hopefully you were able to follow along. It might be worth pausing, rewinding, kind of watching bits and pieces of this video, but there is a practice problem involving projectile motion for you to try after a little bit of graphing. And there'll be an answer key as well as videos going over those practice problems posted